All right, well, let's embark upon motion that is not just in one direction, but in two directions. And when motion is launched in two directions, in the presence and only the presence or force of gravity, we end up calling that free fall. This makes sense. If I throw a marker or any object, it will fall, but it falls at that arc. Because it's trying to move sideways, but at the same time as it's trying to move sideways, it's being pulled down by gravity. And when this happens, it's really two separate motions happening simultaneously. If there were no gravity and I were to throw an object sideways, if I were in space, the object would continue just traveling sideways forever. Nothing pulling it down. Nothing altering its pathway. Now, the thing is, because it's on Earth, it is, as it's moving sideways, pulled downward due to the downward acceleration. And that motion, the downward motion, as it's moving sideways and it goes in the downward motion, the downward motion is as if it were just falling, having no sideways motion. So when you see that parabolic shape of an object falling or being thrown in the air, when you see that pathway, that parabolic pathway, that is really the combination of constant motion, sideways motion, constant speed in the x direction, whereas the y direction is just downward acceleration. But those motions, again, combine. It's kind of like an Etch-a-Sketch. I don't know if you've ever had an Etch-a-Sketch where you turn the one wheel and you do the sideways sketch, and turn the other wheel and you do the up and down sketch. But if you want to make a curve, you're going to have to do kind of both sketches or both wheels at the same time, but they are independent of each other. What you do with the one side doesn't really affect how you do the other side. They're independent motions. And so when we analyze projectile motion, we have to do exactly that. We have to analyze the separate motions, but there is a common link between the motions. So let's go through a problem and see how that all works out. Let's pretend we have an object rolling off the side of a table. Now that object has a velocity initially of 4 meters a second, and it's at a height of 3 meters off that table or wherever it's on. And it's going to roll off and, hit the ground. And I have two main questions that I want to answer. Actually 3, but I'm going to hold the third one for a minute. Well, how long is it in the air? And how far does it hit from the base of that table? One of the first things you have to do in these problems, of course, is define where's your 0 point, where's your origin. And I typically find it's best to make your origin at the very start of the x, but also the lowest part of the problem, if possible. A lot of people are going to say, well, Tapper, it started up here. And yeah, that could be your origin. That's fine. But remember, your origin doesn't have to be the actual physical starting point of the motion. So I'm going to pick this as my origin down here. And I'm going to keep in mind, I'm going to have, a little coordinate plane, because I need to know frame of reference. I need to know that this is going to be positive x and positive y with the directions we typically keep to the right. Positive, up, positive. And what I need to do is understand that this motion is really two motions. It is x motion. And when you're traveling sideways, the only thing that is valid about that x motion is it wants to be, if gravity were turned off, it wants to be a nice constant speed. There is no push or pull. When things are in the air and flying, there is no push or pull sideways, assuming we ignore air resistance, and we are going to ignore air resistance. The friction due to air, because the friction due to air would slow you down in the real world. But in this ideal situation, there are no forces sideways. There's no forces slowing this down or speeding this up once it is released from whatever launch situation was given. Meaning this is no longer in contact with your hand or any other mechanism that launched it. So it's free fall, projectile motion. So sideways motion, the only valid formula is the x speed is constant. The x velocity is constant, and that's going to be equal to change in distance over change in time in the x direction. And we can ask ourselves, well, what information do I have in the beginning of the problem? Well, I know in the beginning of the problem I have a velocity of 4.0 meters a second. But I don't know anything else. What I have to realize, as this thing flies through the air, that sideways velocity, as it's flying, if I were to freeze frame that ball anywhere along the pathway, that sideways velocity, I should be shortening my arrows to make it consistent with my little arrow here, would remain constant. That would still be, Vx would still be 4.0 meters a second. Vx would still be 4.0 meters a second. And same thing down here. Right before it hits the ground, it would still have that sideways motion of 4 meters per second. But as it's falling, of course, it's being pulled downward. And when it's pulled downwards, it's as if this were just dropped and it would go straight down without the sideways motion. And so the y motion, because it's only under the influence of gravity, we have acceleration. There is no acceleration in the x direction. There is gravitational acceleration in the y direction. And so we have to go through our little table. We are accelerating. And you'll note I do something here. I say, okay, well, what's a change in y as it falls? What's its initial y speed? That's a little different than just initial speed overall. It has initial speed, 4 meters a second, but that speed's in the x direction. What's going on in the y direction? We'll find out. What's the final y speed right before it hits wherever we're analyzing? In this case, we're trying to get it to the ground. So what's the final y speed right before it hits the ground? What's the acceleration as it falls? Well, the acceleration as it falls is a constant 9.81 meters per second squared downward. No matter where it is in the fall, it's always being pulled down by gravity. So the acceleration here, right before, the acceleration is consistent. And because it is downward, we're going to make that acceleration negative. Okay. Well, in this problem, we know some information. We know we fell 3 meters. We went straight down 3 meters. Okay. Well, that means that delta y is minus 3.0 meters, right? Because downward, we said is moving downward is going to be negative. The initial y velocity. What's the y velocity? When this falls off this way, what's its up and down motion right at the point where it just falls off the cliff? Well, none. At the top of the cliff, right as it's about to fall, it's not moving up or down at all. It's about to. It's almost like it's at the top of flight. And when you throw something up and catch it, at the very top of flight, that velocity, for a moment, on the up and down direction is nothing. And so we know that happens to be 0 meters a second. What is the y velocity right before it hits the ground? Well, I'm not being asked about it right now. I could find it, but I'm not asked about it right now. I am asked about the time and this distance. Well, notice what happens here. I want to know this, and I want to know, and I can put here, hold on. This time. And of course, I do want to know delta x. And delta x can only be found from the x direction analysis. But what's the key here is that the time of this thing falling and moving sideways, of course, remains constant for both motions, meaning as I move, if I move 1 second this way, I've also moved 1 second this way. And so the time, if I go from here to here, as I move this way sideways, it takes a certain amount of time. That's going to be the same amount of time that it goes from here to here, downward. So time is the link. Time marries the two motions together, because those motions, the sideways motion and the up and down motion, are happening at the same time.
In this video, I'm going to roll the ball down the ramp. I'm going to drop the ball at the same time the ball leaves the ramp. And you'll notice as they're falling, they fall in the exact same amount of time downward. Here goes again. It takes the same amount of time for the ball rolling sideways as it does for the ball dropping straight down to reach the ground. So time falling in the air is the same.
So now, depending on the problem, you have to decide, do I have enough information in the y direction to solve for things? Do I have enough information in the x direction to solve for things? And if I can get enough information in one direction, I can probably find information in the other direction, assuming we link the times together for the same identical motion. And so in this case, I want to know the time. I can find the time. We have a couple options here. This one is going to be a pain, but I'm going to use the y motion here. Let me get the periodic table out of the way. And so in the y direction, we're going to use delta y equals velocity initial t plus 1/2 a t squared. The y velocity, now this is the y velocity, so this is vy1, and that's nothing because we had no y velocity in the beginning, up and down motion. And so we can plug in and find time. And when we find time, we are going to get an answer. So hold on. Should have my calculator out ready. Sorry about that. So .782 seconds. Okay? And what the wonderful thing is, now that I know that it took a little over 3/4 of a second to fall this distance, I can utilize that time now up here and find the x distance traveled. By the way, that x distance traveled we call the range. What was the range? So if you ever hear that or see that terminology, range, it's the x direction traveled by the projectile. And so I can plug that in. So now that I know the time is 0.782 seconds, I can use that here, 0.782 seconds. And now that I know that, of course I can plug into this little formula, and this is the only formula you can use for the x direction. I can plug into that, and 4.0 equals delta x over 0.782, delta x equals, and I can solve that. Here we go. 3.13 meters. So we flew sideways 3.13 meters. So this way is 3.13 meters as it flew 0.782 seconds. Okay. All right. Thank you, and hope this helps with the start of projectile motion problems. This is an easy one, and I didn't even go full. Next lesson, we're gonna use the same thing, and we're gonna find the final velocity right before it hits the ground, vector style, and then we're gonna go into other more complicated launches. Fun times.